All right, we're here to talk about section 7.4, and it's hypothesis testing for regression, or hypothesis test for regression. And with these, we have a couple different ways we can do it. And we'll choose to focus on testing the correlation coefficient, because we've been finding the correlation coefficient for a longer time. So our null hypothesis with these ones, I think this is rho is equal to 0. Anyway, but this is kind of our correlation coefficient for the population. And it might not be exact on that, but it's not super important what the Greek letter is. Anyway, so our null hypothesis, again, that rho is equal to 0, and that means there isn't a relationship between the two variables that we're testing. And then with the alternate, we have some options here. If we want to test that there is a relationship, we do this not equal to 0, which is two-tailed. And then we can also test whether it's a positive relationship or a negative relationship. And so right-tailed test is positive, left-tailed test is negative. And you kind of think of this maybe as the slope of these ones would be negative, so it's less than 0. The slope of these ones, since it's a positive relationship, would be greater than 0, because our line would be increasing. So just kind of a way to think about that. So you have to pay attention to your alternate hypothesis as to figure out what kind of tail you have, and then when you're figuring out your p-value. So on your formula sheet, there's a new player introduced here. There's a couple ways this is done. This is the way we have it written on the formula sheet, so this is what I'm going to use. R is our correlation coefficient, N is our number of pairs of data. Anyway, so we have R times the square root of N minus 2, which this is actually the degrees of freedom also, divided by the square root of 1 minus R squared. And that gives us a test statistic. And then when we're testing, we're following kind of the same process we've had. We've got null and alternate hypothesis. We'll draw a picture, calculate our test statistic. We're here. And then we'll calculate the p-value. And since this is a t-test statistic, we'll be using the t-distribution ones. So if we're left-tailed, right-tailed, two-tailed, we've been working with those a little bit, so we'll just use the appropriate one. And then the degrees of freedom for bivariate data is n minus 2, where n is the number of pairs of data. And then we make our decision, comparing our p-value to our alpha, and then interpret it. And so for these ones, a lot of times it'll say there is enough evidence to conclude there is a relationship, a positive relationship, or a negative relationship, or there is not enough evidence, or sometimes it says insufficient evidence. So just read them carefully as you're going through that. So I'll look at some questions here, bringing up a WAMAP. The first one, it says hypothesis test for regression, a little different here. Running a regression on 100 pairs of data, you find the correlation coefficient to be 0.354. At the 0.01 significance level, does this show significant correlation? And so essentially what we're asking here is the p-value generated from this less than or equal to this? And if we don't know whether it's positive, negative, we'll just use a two-tailed correlation. So I'll put this over here. Whoop, too far. Snapped it to another screen. How fun. And then I'll bring up Excel here and just kind of track in what we have. So the first thing, we have 100 pairs of data. That's going to be N. Zoom in a little bit here. You find the correlation coefficient, so that is R to be 0. Oops, got an extra one, 354. And then this is our alpha. It doesn't really say that. Maybe hit caps lock. Anyway, so is this correlation, or does this show significant correlation? So I'm going to find a test statistic, the t-value, and this is equal to the correlation coefficient R times the square root of n minus 2. So I'm just clicking on these things, and then divided by the square root of 1 minus, and it's our R quantity squared. I think my mouse might be dying. It's slowly losing energy and messing things up. Anyway, so we get that, and I'll grab that formula from here just so we can have it so you can kind of see where that is. Maybe. There it is. It's coming. I'll just put the formula right over the work. Perfect, right? So that's the formula for this. Really want this guy here. So we use this to figure out our p-value now. And if I were to draw a picture, this is a positive test statistic. So on my little distribution, I've got a deal here, and this is going to be way over here, finding this area. And because we don't know whether it's left-tailed, right-tailed, or two-tailed, we just use the two-tailed because that should give us the biggest p-value. Later on, we might find, we'll know ahead of time. So since this is a positive test statistic, I can use this t-dist two-tail, click on my test statistic, and then my degrees of freedom will be n minus 2. And if I can ever get this done here. So is this value here less than this value? So 0.0003 is less than this, so this is significant. If your value, your p-value is greater, then it's not significant. And I don't necessarily love significant or not significant, but it is the language here that we use, so that's it. But essentially they're asking you, is the p-value you find from the data you're given here less than or equal to this? If it's less than or equal to, it's going to be significant. If it's not significant. So a couple more questions like that, and then we get into ones with some data here. So I'll grab the data, and maybe I have room to do it right here. We'll see. I want to keep the formula close by. Pasting special is a good idea. If you're not doing that, you really should. So we'll just use the Correll function to find our correlation coefficient. And maybe. Then we need to find the number of pairs of data we have, and this one we could possibly count them because it goes 1 through 6, but if you're nervous you can use the count function. And then we're looking at pairs there, so our n is equal to 6 here. This would be a two-tailed test. We don't know for sure whether our test statistic is left, right, or two-tailed at this point. So it is going to be our correlation coefficient times the square root of n minus 2 divided by the square root of 1 minus, and it's our R quantity, that's our correlation coefficient, squared there. Now here we have a negative test statistic, and this is pretty close to 0, so it'd be something like we have a value here, and then because we don't know, we're going to double this. So for our p-value, it'll be equal to 2 times a t-dist is the way t.dist I'm going to do this. Click on my test statistic, comma, the degrees of freedom is n minus 2, and I forgot to put true. And maybe I misspelled something there. Anyway, battling through it. Our p-value ends up being really large. So when I compare it to this, we are way larger than 0.01. So this is not significant. A little bit of work to do. So again, we're using a function, or we're given these values here. We can either find R and N, or we're given them, find the test statistic, use some knowledge we have to find our p-value, and then compare that to our alpha. If our p-value is less than or equal to alpha, then it is significant. If our p-value is not, then it is not significant. We'll do a few more examples in another video. Thanks for watching.